The last part of the introduction is the probability review. It might be a little bit dry, but make sure that you know about all of the concepts. And the slides are up on Moodle, so check them out whenever. So first of all, we need to define and review events and partitions. And so definition of partition, the collection of sets, H1 to HK is a partition of another set, H, if 1, the event set is joint, which we write as the intersection of HI and HJ is an empty set for any I not J. Second, the union of the sets is the sample space, H, and which we write the union of all of HK will be the big H. Okay, so already saw a partition earlier about whether someone has breast cancer or not. Okay, it's a partition of 2 sets, cancer or no cancer. Okay, and in particular, first of all, they're disjoint. There's no overlapping, but also the union of it is the entire sample space because you have no other people not falling into any of those 2 sets. Okay. So really quickly, any examples I can think of, partitions, real life, or any other encounters of other coursework? Yeah. Yeah, no, you go first. Yeah.
Age groups.
Age groups.
Age 1 to 10, 11 to 20.
Right.
Up until you include the oldest person alive.
Right, and then there are just the age groups, and then yeah. So that will be yeah, especially in terms of a survey, it's gonna be a multiple choice. I mean, I would say multiple. Yeah, like multiple choice. That you're just gonna pick one category of yourself, right? Okay, good. Yeah, and I guess someone was trying to speak up.
Yeah, I was gonna say even and odd numbers. That's
even odd numbers. Yes. Yeah. So they are another great example of partitions. Great. Yeah. So at the end of the day, make sure that they're disjoint in the first place, and then the union is the entire sample space, and then you're gonna have a partition. And you can see that partition is particularly important in Bayesian inference. And you need to have a partition first, otherwise, first of all, like the law of total probability wouldn't even work because you need to have a partition first. All right, so the n-science of probabilities, there are 3 of them. And for us, the most important 3 are here. The rule of total probability, we talked about it before, is just if you have a partition, then the sum of each of the set of the partition, the probability of each of the sets should sum up to 1. Okay, so that's actually by definition of partition, you have to satisfy that. The second one is the rule of marginal probability. I'm going to pause here for a little bit so you can reason through why the rule of marginal probability makes sense here. And we're using this, remember earlier, to try to come up with the marginal probability of the denominator. Okay, so I'm going to just pause here. You can talk to your neighbor really quick. So does it make sense? The rule of marginal probability means so we're trying to get the probability, marginal probability of E, and then you can get it from the law of total probability, which is in the middle part. And then all of these are joint, okay? And in order to get the joint, you can do the product of the marginal and the conditional. Okay, so base rule, when we get to the third, is always, you're trying to get the reverse conditional probability. As earlier, you start with each of the HK or HJ, and then you have this marginal of E, and then I want to know, conditioning on this specific event E, I want to see my updated belief about a particular set. So earlier for the breast cancer screening example, we only have 2 in the denominator. So it's a sum of 2 joint, and each of the joint is the product of its corresponding marginal times its corresponding conditional. And then earlier, the generic form I showed you earlier, when it's continuous, it's just going to be an integral. Okay. All right, sounds good. So those are pretty related to what we did as the example. So hopefully they're intuitive to you right now. And for Bayesian inference, I just want to show you something that a lot of times, so earlier we're talking about sets, but sometimes in actual inference, they might just be different and disjoint hypotheses or states of nature that you want to make inference about. Okay, so they're unknown. And you're still going to get this E. We just still use them as the outcome of a survey, study, or experiment. Earlier was a particular event. Here it's probably just the data that we can collect from the study. So if you want to compare those hypotheses post-experimentally, in a sense that it's after you collect the data, the intuitive thing to do is to look at the ratio of their posterior probability, right? Posterior in this case that these are the data, and I'm comparing specifically two hypotheses, HI and HJ, out of my partition. So if you do the math a little bit, so I'm just showing you here, because each of this, each the denominator and numerator, you can use Bayes rule, right? Because it's a conditional probability, and specifically just the Bayes rule that you have. So you will get the ratio like this. And in particular, you can see that because using Bayes rule, you always have to divide by the marginal probability of the event. So those two can cancel out. When you keep deriving this, so let me get to the second part. So what you are left with, if you look at this, is the event given hypothesis I, that's a conditional, times the marginal of hypothesis I over the product for J. Okay? And if you further break it down, pretty much just like break this into two. You have two ratios. The one on the right, we actually can define it because it's the ratio of the priors, right? That's before seeing any data. And the remaining part of the left, we actually call it Bayes factor. Sorry, I forgot about space in between. We should just have the space in between. Bayes factor and then prior beliefs. So a lot of times, Bayes factor can be used to determine which one is more likely or not. Okay, when you're trying to do Bayesian inference, comparing to disjoint hypothesis, then at the end of the day, the ratio of the posterior actually becomes the product of Bayes factor and the ratio of the prior belief. And sometimes if you give a uniform prior because you don't have particular preference of one hypothesis over the other, this might just be one, okay, because they're all equally likely. And then what matters in this case is going to be the data. Because what each term is about, if you think it more, this term is telling us that if HI is true, how likely it is to have my data, right? And the same goes for if HJ is true, how likely is my data? Okay? We're always comparing. And then in this case, especially if you have the same prior probabilities for both hypotheses, then at the end of the day, posterior is determined by the data itself. So this is just a mathematical formulation for you to see how things work out. Bayes rule does not determine what our beliefs should be after seeing the data, but it's more about how they should change, right, from the prior to the posterior. All right, so this set of stuff, a bit dry as well. I probably won't read them through. For univariate random variable, we start with the cumulative distribution function, CDF, and then I list in the table for you the discrete and the continuous case. Okay, so those, you can always refer to those slides as reference. And I think the key here is that they should be well defined. Okay, so for the discrete cases, sum of the probability is 1. Continuous cases, the integral should be 1. And then you need to know how to do the expectation. So those are the two at the bottom. And in particular, the last row is about the expectation of a function of this random variable. Okay, so those, I think either in Math 241 or Econ 209, you have seen this before. So we will use this periodically throughout the course. Okay. So that's for the univariate random variable. And we also care a lot about joint, as you can see. Later on, it's not only about the joint of the data and the prior, but also sometimes if in the model that you have multiple parameters, we also care about the joint. Because we need to know how to write out joint distribution. So this again, pretty generic. What I would say to pay attention to is all of those, how to come up with the marginal. And we have seen this on the discrete case just now, because even if you're just trying to use the base rule, you have to figure out how to come up with the marginal distribution. Okay. So if you have, in this case, joint x and y, in order to get x, you use sum over y for the discrete case, and for the continuous case, you integrate out y. So those are key, I think, are pretty important throughout this course as well, this joint distribution. And then, of course, from there, we get conditional distribution. So all of this, I would say a little bit tedious, so I wouldn't go into all of the details in class, but those are good references, pages for you whenever you're trying to deal with certain manipulation of those algebra and calculus. So those are important. Refer those back whenever you need it. And one more thing, pretty important here, is transformation of variables. Okay, so maybe when you're learning it back then, you don't know why you want to do it. But for the Bayesian point of view in particular, if I have a random parameter follow a particular distribution, something that we always going to see throughout the course will be, so for the normal distribution, we know that it has two parameters, mean and standard deviation, right? Or like variance. And a lot of times, in order to do all of those calculations a little bit more easily, what we do is, so normal, we have, this is just an example, not the one that on the slide, but normal has, so we say the random variable y follows a normal distribution with mean mu and standard deviation sigma. And so this is standard deviation, and sigma squared is the variance, right? So sometimes you might work with variance, sometimes you might work with sigma, then the transformation of variables is important, okay? Another example, still in the normal field, is that a lot of times, instead of working with sigma or sigma squared, we work with precision. You probably haven't heard the term before. Precision, sorry. We use P, and it is defined to be the inverse of variance. Okay, so this later on you will see that it turns out to be much more easy to work with when we're deriving all of those normal cases. So this again is a transformation variable. Okay, because from sigma to sigma squared, it's x to x squared, right? And then from sigma to phi, it's going to be 1 over x squared. So you need to know those distribution, you need to know those transformation, and then say, if I know sigma follows the distribution of what, you will need to know how to derive the distribution that phi will follow based on the transformation of variables. Okay, so this is why we care about it early on. And when we get to those points, we're going to do those review as well. But here, really quickly, suppose x is a continuous random variable with PDF fx. Then if you have a gx function is monotonic and differentiable, then this y, which is g of x, has this particular PDF. Okay? So this is a formula covered in probability. And in light of time, I don't think I will cover the example today. But the example that I want you to try on, you get the chance between now and next week, is that if you have an x random variable is a uniform between 0 and 1, asking you to come up with the function gx, which is negative ln x. Okay? So we don't have time to do it now, but this is the case that you have to think about, well, whether negative ln x is monotonic and differentiable. Okay? If they are, you will be able to use this particular formula that we put in the middle to derive the PDF of this new random variable. Okay, so practice that when you get the chance. Tuesday when we come back, I'm gonna walk through this and then finish the review and start the new lecture of the new unit.